Hi, I'm Nikil, and I'm going to be presenting our work on dataset construction biases of social bias benchmarks. This is joint work with Saniba Dev, Daniel Kushabi, Tushar Kode, and Kai Wei Cheng. The growing popularity of pre-trained LLMs has amplified concerns about the social biases that might be exhibited by these models. In response, the community has proposed various benchmarks to help quantify these biases. A popular recipe looks like this. You pick a downstream task, say co-reference resolution or natural language inference. You develop a curated dataset that helps you pick out the kind of biases you're interested in analyzing, so say gender occupation bias. And then you provide an accompanying metric, say predictive accuracy, to help approximate the social bias. And these benchmarks are widely used by machine learning practitioners to compare models for social bias before deploying in real-world applications. So here's an example from a popular benchmark, Winogender, where the downstream task is correct. The dataset here consists of Winograd-style sentence pairs that only differ in the gendered pronoun, and the metric is mismatch in predictions. So let's consider an example here of male-female disparity. The sentence here goes, the electrician warned the homeowner that he might need an extra day to finish rewiring the house. The other sentence is the exact same, except for the pronoun he is replaced by she. And in this case, since the model exhibits a disparity in prediction between these two sentences, we say that the model exhibits gender occupation bias in this instance. But here's a natural question. The choice of sentences in this curated dataset is arbitrary, right? So what if I, as the dataset creator, had chosen to craft my sentences slightly differently while still maintaining the essence of the social bias? As a concrete example, consider this. I've gone ahead and changed the verb warned to cautioned. Now, of course, the sentence pretty much means the same thing, except we see that the model, in this case Spanbert, has now changed its prediction on one of the sentences, and now suddenly there's no longer a disparity, and hence suddenly the model no longer exhibits gender occupation bias in this instance. Alarming, right? What is going on here? Well, there's a hidden benchmark assumption here that any change in the CoREF model's prediction after changing pronouns is because of the gender occupation bias. Now, this is only true for a model with near perfect language understanding with no other biases. However, we know that models in the real world often demonstrate many other biases, say positional biases, where you want to resolve the pronoun to a nearby noun, and other spurious correlations. That leads us to our motivating question. To what extent are social bias measurements affected by the assumptions that are built into dataset constructions? Or put differently, how reliably can we trust the scores obtained from social bias benchmarks as faithful indicators of problematic social biases in the model? Now, as we see in our work, the answer is unfortunately not very much. In this work, we empirically simulate various alternate constructions for two popular benchmarks, Winogender and BiasNLI, using seemingly innocuous modifications, and we show that they have surprising effects on not just the measured bias, but also perceived model ranking. Here are some concrete examples of alternate constructions. So one such alternate construction that we explore is negation. So say we change the verb from the doctor bought to the doctor did not buy. We of course expect that this should not have any significant effect on the measured gender occupation bias. Another example is adding a descriptor such as an adjective. So if we replace the doctor bought an apple to the doctor bought a red apple, once again, we expect this to have no significant effect on the measured gender occupation bias. However, our results say otherwise. Here is a plot on Winogender. Each tick on the x-axis here corresponds to an alternate construction, and the different lines with different markers and colors correspond to different models. Clearly, we can see that the different alternate constructions result in vastly different measured biases in these models. Now, there are plenty of interesting observations to be made from this plot alone. One such observation is that it is not only possible to discover varying levels of bias for the same model, but more interestingly, it is also possible to observe changes in perceived model ranking across these alternate constructions. For instance, consider the long-former model and the Spanbert model. Now, in the original construction, the long-former model appears to be more biased than the Spanbert model. However, once you start to add adjectives before occupations, we suddenly see that the ordering is now reversed and the Spanbert model appears to be more biased. We observe similar results in BiasNLI as well. To conclude, our empirical evidence shows how the model's non-social biases, which in our experiments are brought out or masked by alternate constructions, can cause bias benchmarks to underestimate or overestimate the social bias in a model. Now, this highlights that these bias measures can lack concrete definitions of what bias associations they actually measure, and consequently, the relation between measured bias and experienced harms becomes very unclear. This work results in a lot of interesting next steps. For starters, we encourage both syntactic and semantic diversity in the sentences that are used in these templated benchmarks. It would also be fruitful to provide uncertainty measures surrounding measured bias as opposed to just providing a single number. Another exciting future direction is to explore constructing benchmarks that operate on faithful explanations of the model's predictions rather than the predictions themselves. Overall, we hope that our troubling observations about the fragility of these existing bias benchmarks motivate more robust measures of social biases. Thank you.